Hi everyone. Have you ever wondered how threat actors can leverage your vulnerable web servers to spread malware and achieve their malicious goals through widespread campaigns? Have you ever wondered about the techniques that they use, the vulnerabilities that they exploit, and the samples that they deploy? You might even have wondered how you can expose this activity in your own data sets. So over the past year, Imperva Threat Research has been attempting to answer these questions, and we want to share the framework that we've developed and some of the campaigns that we've uncovered using these techniques with you today. So my name is Daniel Johnston. I'm a security researcher within the threat research group at Imperva. My domains of specialty are web application security, bot detection, and malware analysis with threat intelligence.
Hello, can you hear me?
Is your mic working?
I'm not sure.
Yes.
Now it's working. I'm Owen Akar. I'm also a threat researcher at Imperva. I'm 16 years at Imperva, and my interests are big data and data science, and my domains are both web application security and database security.
So I'm going to talk a bit about the agenda. In the introduction, I'm going to talk about the data that we collect at Imperva, along with some of the challenges that we have in that data set. I'm also going to talk about how threat actors leverage web application vulnerabilities for malicious gain and to deploy malware campaigns. Then I'm going to move on to talk about the framework that we've developed for automating malware handling. I'm going to talk about how we identify malicious samples and malicious URLs in our large data set. And then I'm going to talk about how we safely handle those samples. Then I'm going to hand over to Ori, who's going to talk about malware campaign identification using machine learning clustering and using anomaly detection. And then finally, I'm going to move on to talk about some of the campaigns that we've identified using the frameworks that we've developed. Okay, so on to the introduction. So one of the flagship products that we have at Imperva is our Cloud Web Application Firewall, or Cloud WAF. And within the Cloud WAF, we have the Imperva proxies and the security engines located in points of presence all across the globe. So the point of the security engine is essentially to mitigate malicious traffic from malicious actors, while simultaneously allowing legitimate traffic from benign actors to pass through to the origin web server. So we see billions of malicious requests every day, and we store those events in our threat research data lake. And as you can imagine, it amounts to a huge amount of data that we can then leverage for threat intelligence. So I want to talk a bit about how threat actors can leverage web vulnerabilities for their own malicious gain. So at our work in Imperva, we see many different threat actors leveraging many different types of web vulnerability for various different objectives in the pursuit of an ultimate goal. And I don't have time to go through all of the different attacks with the different objectives, but I want to focus on web vulnerabilities, RCE web vulnerabilities, in the pursuit of malware deployment to achieve objectives like ransomware, deployment of crypto miners, and botnets, just for an example. Okay, so in a report published by Verizon Business, their data breach investigation report, they actually outline just how important of a target web applications are for threat actors. So about 40% of the top action vectors in data breaches can actually be attributed to web applications. So furthermore, in non-misuse or non-error breaches, over 20% of these breaches can be attributed to web vulnerability exploitation. Furthermore, they go on in their report to outline some web vulnerabilities that are commonly used or have been commonly used in the past year in data breaches. And among those are vulnerabilities in Atlassian, in MoveIt, Manage Engine, and Sugar CRM. And these are vulnerabilities that we're very familiar with in our work at Imperva and have been working to mitigate them over the past year or two. So I want to talk about a specific example of an RCE vulnerability. I think we've lost the screen here, but I want to talk about a specific example of an RCE vulnerability that we might observe in our dataset at Imperva. It's an exploit attempt of the vulnerability CV 2024-4577. And some of you might already have recognized it as an exploit attempt of the PHP CGI vulnerability that was disclosed earlier this year. So actually, the guys who found this vulnerability were actually present at the Black Hat conference earlier this week, and they actually talked about this vulnerability and some other vulnerabilities that came about because of it. So essentially, the vulnerability allows a threat actor to append a soft hyphen, denoted by the %AD in the screenshot there, surrounded in red. It allows the attacker to append additional parameters to the query string of the request, which essentially instructs the web server to treat the post body as PHP code and execute it on the server. So in this case, the attacker is invoking PHP system, which then invokes MSHTA to download and run a Microsoft HTML application. So this is a great example of threat actor activity. It's quite interesting, but there's some clear limitations here. We don't know what the file is that's being downloaded, and therefore we can't deduce any objectives of the attacker because we don't know what they're trying to do. So that leads me on to talk about the limitations that we have in our Imperva dataset. We have no access to the endpoints, so we can't see any installation of the malware on the asset. We can't see any communication between the command and control server and an infected server, and therefore we can't deduce any actions on the objectives. We don't know what the attacker's intent is. Really, we can only see the first 4 links in the cyber kill chain. So clearly some enrichment is required to be able to reveal the real intent behind the actions of the attackers. So that leads me on to talk about the framework that we've developed for automating malware handling. So this is a very high-level diagram of the framework that we developed, and I'm working from left to right here, but as we know, threat actors will send malicious requests to sites and assets protected by the Imperva Cloud WAF. We will store all of those malicious events as logs and will in our threat research data lake. So on this huge quantity of data, we will then apply some fairly sophisticated ETLs and queries to be able to extract out the malicious URLs. We'll send those URLs to a sandboxed environment where they're downloaded. Some basic processing is applied. They're zipped, they're hashed, and they're stored in our isolated cloud storage. And then those events are, we get the metadata from those samples, and we re-import those back into our threat research data lake. So then we can cross-correlate between the firewall events and the samples themselves. The final piece to this is our enrichment from open source. So we use APIs like the VirusTotal API to then enrich the information that we have about the samples. That gives us a very rich set of data that we can then apply further processing to. So we have some challenges when it comes to extracting URLs from like a large quantity of HTTP data like we have. And one of the main challenges is the number of false positives that we observe if we try to extract the URLs. So lots of false positives can lead to a lot of time spent filtering and less time actually analyzing an interesting sample or investigating an interesting campaign. So the solution that we came up to this was to actually split the URLs into 3 different categories. So firstly, we have IP-only URLs. These are URLs that don't have a registered domain. And what we noticed is these URLs are much more likely to be malicious than other types of URLs, for example. So we extract those directly, and we apply some heuristics to filter out the final false positives, and we send them to our downloader environment. Secondly, we have regular domains or regular domain URLs, which, as you can imagine, if you try and extract those directly from a large HTTP dataset, you're going to get a lot of false positives. So what we do is we actually extract the command injection from all of the malicious HTTP requests that we see, and then we further extract the URL from that. And this allows us to filter out a lot of the false positives. We then apply a set of heuristics to those URLs to filter out some final false positives and other scanning domains that we're not that interested in. And then we send those to the downloader as well. And the final set of URLs that we handle are referred to as lots, or living off trusted sites. This is a project that's actually external to Imperva, but it basically lists a lot of services and sites that are legitimate by nature, but have been known to to host malicious files in the past. So things like GitHub user content, things like pastebin, and things like OneDrive and Google Drive, all legitimate services, but they can host malicious files. So we handle those in a separate way. We apply a separate set of heuristics, and then we send those URLs to the downloader. Handling the URLs in this way allows us to strike a nice balance between being too permissive and having too many false positives, and being too restrictive and potentially missing interesting samples. Okay, so now that we have our malicious URLs, we can send them to our downloader environment. And for that purpose, we have a Dockerized Python service, which essentially will download, process, and store each of the samples. So each of the samples is stored as a zip file, a password-protected zip file, and we name it with a SHA-256 hash of the sample itself. This allows us to easily retrieve it and do some manual analysis if required afterwards. So baked into our downloader service, we have something that we call second stage URL detection. And that's, so for web delivered samples especially, we see a lot of textual samples, things like bash scripts or PowerShell scripts, which are essentially downloaders for second stage binaries. So what we did was we would apply a regular expression to these textual samples to try and extract the second stage URLs. But what we soon found was that for textual samples where URLs are split between parameters, for example, a regular expression is just not going to cut it. So that's why we came up with LLM second stage URL detection. Essentially, we send the content of a textual sample along with a prompt to an LLM, and this is generally pretty successful at reassembling the second stage URLs, and then we can take those and send them to the downloader. Okay, so just to summarize how we get the enriched data set that we have, Imperva has a large volume of events, malicious events that we store in our threat research data lake. From that vast volume of data, we extract the malicious URLs, we send them to an isolated environment for downloading and processing, and then we re-import that metadata back in so we can cross-correlate between the firewall events and the samples. And then finally is our enrichment from open source. So we use APIs like VirusTotal and sandboxes and honeypots to then further enrich the data set. So that gives us a great platform to then do further processing and extract further value from the data. So at this point, I'm going to hand over to Ori, who's going to talk about the anomaly detection and the malware clustering that we then apply to this enriched data set.
Thank you. Can you hear me? Yes? Okay, so I will go to more technical parts, and I will tell how we detect interesting anomalies inside of our data to find interesting campaigns. And later I will talk about how we do ML clustering, cluster attacks into campaigns. So first of all, I will start with our anomaly detection system. Here you can see a chart where you can see the requests or attack requests over time for a specific CVE, so specific CVE and a specific client. What is a client? Our Cloud WAF classify all the requests that we get into clients. We have different different attacking clients that they can be browsers and they can be hacking tools and others. And in this case, you can see that the ID of the client is 589. We have something like 1,000 clients. So what you can see here is a counter for the number of the requests over time for this specific CVE and this specific client. And you can see that in the middle there is like a peak for 2 days with something like 100K attacks. So this is something that we found using our anomaly detection system. And this is a point for a drill down for researcher. We know how to correlate between an anomaly and a malware campaign. So we can see the anomaly, we can click on it and get to the campaign and then analyze the campaign. So this is like an entry point. We can now look at the data, we can look at the payloads and understand what happened there. So let's look at another example. Our anomaly detection system has many counters, and one other counter that I wanted to show is the number of requests, again attack requests, for an injected URL or IP, and in this example you can see an IP injected to our data. This time it took something like 2 weeks, and you can see that in the final day we got to something like 800K or 600K requests for a specific day. And again, we found this in our data. Again, it is a point for a drill down. We can now look at the campaign and understand what happens. And the anomaly detection system helps us to find the interesting campaign, interesting valuable insights inside our data, not only for malwares. So let's talk on how we find such anomalies. So we have a solution which is completely serverless. We used a managed query engine and managed cloud function to do collection, aggregation, and anomaly detection on our data. The result of it is hundreds of counters, like what we've seen. We count the number of requests for a CVE and client, injected URL, and much more. And we have, at any time, 20 million anomalies that we can browse inside of our database. So let's understand how it happens. So this is the data flow for our anomaly detection system. We have a data lake, like Daniel explained before. The data lake has thousands of tables and terabytes of data added daily to the data lake. And we have counters. I will explain very soon how we define these counters. And the idea is that we collect the data by reading the data from the source table into dedicated counters table inside of our anomaly detection system. We read the data from the source table exactly once. Why we do it once? Because reading data from source table is considered heavy. We perform aggregation and filtering, and it might take a lot of resources, so we prefer to do it once and hold the data, redundant data, inside of our counters table. Once the data is in our counters table, we again use cloud function to do the aggregation and to do anomaly detection. I will explain how. But everything is done inside of dedicated tables, which can be explored using our query engine. So let's understand how a researcher can define counters. So we have JSON configuration files. We call them datasets. And a dataset is simply a list of counters where each counter is like a SQL statement for getting data. For example, a CVE over time. So I will get data for all of the CVEs that we protect against over time. Okay, so it will be something like we will choose the CVE, and later we will group by the CVE. The CVE will be the key, and I will hold the numbers for all the CVE, daily, hourly, and so on. So eventually, a data set is like a group of counters. For example, if we have a CVE's data set, we will have a CVE counter or CVE plus client counters and so on. And we have hundreds of counters, not only for malwares, but we use it also for malware detection. How we do the anomaly detection? Again, we are completely serverless. We have managed query engine, managed cloud function, no servers. So what we have is SQL. We do it using SQL, and we are using Trino as a managed query engine. And I strongly recommend to all of you, if you are using, and I believe you are, using a query engine, look at the functionality it provides. Look at the docs, because today query engines are very powerful, and I will show you some example of what we do. So let's look at the first example of how we do anomaly detection using SQL. The first example is pretty simple. The first step is to collect the data from our dataset. The data is already collected and saved in our database, so we query the data for a specific dataset. We query all the counters, all the keys, and hold them in memory for a certain period of time. For example, 90 days back. Later, we calculate statistics. And in this case, we calculate the average data per counter and the standard deviation. The last step is to find anomalies. And in this example, I defined anomaly as a value bigger than the average plus 2 times the standard deviation. Now, it's very important to understand we traverse billions of records. And the data doesn't leave the database, which means it's very efficient, billions of records in just minutes, and it's also very cost efficient. Let's look at another example. The second example, I used the match recognize function, which is supported by multiple databases. The match recognize function gives us to query data according to patterns. And I created like a pattern, for example, where there is a start value. Then I request that the value will go up at least 4 times and get to a final value. And there are some restrictions for the final value, which has to be 3 times the start value and 2 times the average value. So this is a pattern, and it is like it's like a regular expression language that you can use to find patterns inside of your data. Again, traverse billions of records in just minutes. You can find V-shapes in your data, U-shapes, and we use it to find like peaks and regular peaks in our data. And again, you can traverse billions of records in just minutes. So it's very effective and very cost effective. So that's it about our anomaly detection system. I will move to malware clustering. So first of all, why are we clustering malwares? We have like millions of requests every day only for the malware injection, and we have to somehow show it to our security analysts. So we are not going to show them millions of requests, we want summary. So what we do is to cluster data, and you can see some examples how thousands or tens of thousands of records are clustered into a single record, where we have like start time, injected URLs, and a lot of other columns that we finally present and say, this is the malware campaign. You can decide if you want to analyze it or not. So let's understand how it's done. We are using the same technology stack that we like. We have managed query engine and we have cloud function. And in this case, the managed query engine helps us to group the attacks, group the requests into attacks, and then calculate distances. And I will explain in the next slide how we calculate distances between attacks to understand how far attacks are from each other. So this is a very heavy operation of calculating distances, but again, we are doing it using SQL. Data doesn't leave the database. We don't have Python processes, and we don't need to load data frames and so on. Very effective and very cost effective. Once the distances that I will explain how we calculate are calculated, we save it into some object store, and the data is moved to the next step, which is the clustering algorithm. In the clustering algorithm, it seems weird that we are using cloud function for ML clustering, because ML clustering is normally heavy process, which takes a lot of time and a lot of resources. But because the distance calculation was done by the query engine, it works for us. And 15 minutes of time and up to 10 gigabytes of memory, which are our limitation for the cloud functions that we use, are completely fine, and I believe that it can work for many other projects too. So we take the distances, we load them into memory, run clustering algorithm, and then dump the results back to the object store. Once the results are in the object store, we use, again, SQL. First of all, when we first created the pipeline, we had to fine-tune it, validate it, so we joined the data with the source data and decided how to change it, how to decide which feature to use, and so on. Now that we have the pipeline up and running every day, apart for several days that it failed, I feel, but normally it works, we do a data enrichment, and we have the data ready for our security analysts. Okay, so let's last thing for me is how we do the distance calculation. So we do the distance calculation using SQL. It's a heavy operation. It takes 10 minutes, 20 minutes, but again, it's in SQL, managed query engine. It doesn't cost us much, very effective and very cost effective. So let's look at an example. We take the attack data. Attack data is the aggregated requests data. And we try to look at every pair of attacks to decide on a distance. Okay, so we self-join the data with itself, so we will go over all the pairs, and you can see how we are doing that. And what's important is that we now have to calculate the distance. So we are using different features of the attacks. For example, we check if it is the same client. We have two attacks. Here we have left attack and right attack from the left side of the join and right side of the join. We check if it's the same client. I explained before about the client classification. We use the Levinstein distance, which is also called the edit distance, to see if the injected URLs are the same or close to each other. And we also use the constant similarity function to look at the attack sites histograms to see if the two attacks were done on the same attacked sites. And of course, the real distance function is more complex. We have more features, but this is only the idea of how you can calculate distances between attacks using SQL. That's it for me, and back to Daniel.
Okay. So now that we know how we apply the machine learning clustering and anomaly detection to identify the campaigns in our large enriched data set, I want to talk about some of the real-world campaigns that we've actually identified using this framework. So I'm not going to get time to go through all of the campaigns that we've identified, so if you're interested in that, I would encourage you to check out the Imperva blog on the Imperva website, and you'll be able to see more of the campaigns that we've seen. So the first one I want to talk about is that of the sysrv botnet. So sysrv is a well-known botnet malware written in Go, and it spreads using well-known web vulnerabilities. So we saw like widespread exploitation of Atlassian Confluence and Apache struts, basically propagating this campaign. So the idea behind the campaign is to deploy the XMRig cryptominer to as many vulnerable servers as possible to use the CPU resources of the web servers to mine cryptocurrency. So using the framework, we were able to aggregate together all of the events of the campaign along with all of the samples and all of the metadata, use the clustering algorithm to bring all of those records together for easy analysis for our analysts. Using the framework, we were able to uncover some brand new TTPs and IOCs that hadn't been seen in the wild before, including the use of a compromised domain or compromised website of a well-known Malaysian academic institution. We also saw the use of a Google Sites domain to host the second stage binary. As you can see in the screenshot, what looks like a legitimate Google 404 error page is actually hiding the bytes of a Golang binary. So you can see a big blob of text in the page source. So we were able to extract this binary and do some analysis. We were able to extract the configuration, and we were also able to extract the Monero wallet that was used for the campaign. We were able to see that the threat actors were netting around 57 Monero per year, which equates to around 7,000 GBP, which doesn't sound like a lot, but if you think that they might have multiple of these campaigns ongoing at once, it can amount to a considerable amount. The second campaign that I want to talk about is that of the Tell You the Pass ransomware campaign that we saw propagated using the PHP CGI vulnerability that I talked to you about earlier in the talk. So this is a ransomware that's targeting PHP web servers, and they use the PHP CGI vulnerability to deploy a Microsoft HTML application which was VB script enabled. So within the VB script was an encoded string, which, as you can see in the screenshot, is in the S parameter. So you can see that that's the encoded bytes, or the encoded bytes of a .NET binary. We were able to reconstruct this, decode it, and load the .NET binary into dnSpy for some analysis, and we were able to determine the actions of the binary, what it actually did. So upon execution, it would reach out to a C2 server with a HTTP request disguised as a request for a CSS resource to blend into network traffic, to other network traffic. It also enumerated directories, encrypted files, and then put a ransom note on the web directory of the PHP server. So interestingly enough, it's a ransomware that's actually targeting web servers specifically. Again, using the framework that we developed, we were able to aggregate all of the events of the campaign together along with the samples, apply the clustering, and get it all together in one convenient place for analysis. So the final campaign that I want to talk about, and probably the most interesting one that we saw, is one that we believe we can attribute to APT29, or Cozy Bear. So Cozy Bear is a well-known threat actor that's thought to be a part of the Russian SVR, or Foreign Intelligence Service. So they've been associated with many different high-profile attacks and campaigns over the past couple of years, including the supply chain attack, the SolarWinds supply chain attack, and the mass exploitation of Team City servers last year. The activity that we actually observed, we observed some very targeted and coordinated attacks against Polish government websites back in March. And what they were trying to do is they were leveraging a vulnerability in F5 Big IP, their load balancer solution, to deploy a sliver implant. For those of you who are unfamiliar with what Sliver is, it's essentially an open source alternative to Cobalt Strike. It allows for a lot of different post-exploitation activities on an infected host, including information gathering and command execution. So as you can imagine, in the hands of APT29, it would be a very useful tool given the right target. We also saw some follow-up activity last month in November, where the same activity was happening on the sites of Ukrainian financial institutions. So how is it that we think that we can attribute this to APT29? So for three reasons. Sliver is a known tool used by APT29 according to MITRE and Cybereason. So it makes sense that if they used it in a previous campaign, they would use it again in this one. So secondly, and probably more compelling, is that the C2 that we observed in this campaign was actually observed in a previous APT29 campaign, namely the JetBrains Team City campaign that I mentioned. And then thirdly, only targets of interest to the Russian state were observed in the clusters of this campaign. It makes sense that not only can we attribute this to a Russian threat actor, we can attribute it to APT29. Okay, so on to the takeaways from the talk. So firstly, automation, big data analytics, and anomaly detection provide excellent tools for threat hunting and scale. So if you find yourself in the position that you have a data set like ours, we would encourage you to use the tools that Ori's outlined to be able to extract the value from your data sets. So secondly, threat actors such as the ones that we've demonstrated are regularly leveraging web vulnerabilities for malware deployment. And this is something that we're seeing day in and day out at our work in Imperva, and it's something that's backed up by the likes of the DBIR report from Verizon that we mentioned. So finally, identification, correlation, and tracking of malware campaign activity has real community value. So being able to expose the IOCs and the TTPs of threat groups like the ones that we've seen is of real value to stakeholders in the security community, which allows them to do their own detection and attribution based on those IOCs. And that is all that we have for this talk. I want to thank you for listening, and we'd like to open for any questions that you might have. Thank you.
Thank you so much for insightful talk. I have two questions. The first question is, what type of clustering technique have you been used? Have you compared to any hierarchical and density-based algorithm as well? And the second question is, regarding the different type of the APT group, how many group did you identify apart from the APT29? Thank you.
So I think the first one's for Ori, maybe?
So can you hear me? The question was about the loss function?
So what type, because clustering, we know different type of algorithm. So in your pipeline, what type of clustering have you been used? Is it, and then the algorithm have you been used? Have it been compared with the density-based algorithm? Because I'm doing quite similar research with the APT in terms of IPS. So that's why I'm curious. And the second question is regarding with the different type of APT group.
Okay, so
thank you.
So regarding the clustering, because the clustering is unsupervised, it's hard to use like common metrics, and we haven't used any known metric. Instead, what we did is to take the clusters that we found. We took the clusters, and then we joined them with the source data. Now, joining the clusters with the source data allowed us to define our own custom metrics and then to improve our data over time. I can try to explain it better. For example, we can we can cluster the data and then take the data, the future data, the data that happens after the clustering, to see if the results were clustered together. But all our validation was done using SQL with custom metrics, and we found it like the best way to validate such data, because in unsupervised we don't have like good metrics to do the job for us like in supervised.
Thank you.
Yeah, and your second question about I guess it's about the other threat actors that we've observed. So yeah, it's an interesting question. I don't think that we can give a direct answer to how many APTs we've observed. We're still actually working on the attribution part. As you know, attribution is a difficult thing to do. But certainly it's in the thousands of threat actors that we've seen. So.
Thank you. Great talk. Clearly, SQL's doing a lot of heavy lifting. What flavor SQL Server are you using? Is that on-prem or is that cloud or something in between?
We use the Trino as our managed query engine. And if you are asking, we are working on AWS, and Athena has behind the scene a Trino engine.
Thank you for a great talk. You mentioned earlier during some of the malware sandboxing that you were using LLMs to go ahead and grab more data out of it. What boundaries or guardrails did you put in to prevent things like prompt injection or other kind of like data poisoning techniques that you might see malware trying to do to avoid these kind of detections?
Yeah, so that's when we apply the LLM to try and extract the second stage URLs. So yeah, we use the LLM, and then we actually we don't take just the output of the prompt. We then parse the output of the LLM to further protect us against any injections.
Thank you for the talk. This is purely on statistics and raw technology. So when you distill from the source data down and you index and aggregate for multiple times, what's the final aggregate data reduction rate that you get it down to across all your aggregations?
What's the data?
So you aggregate from source data multiple times in multiple ways. What's the final net aggregate data reduction rate for the final data sets from the source?
What's the final aggregation? So we have several tables. it's like a very generic framework. So we have, for example, we can collect daily data. So we have daily table with a partition. It's all stored eventually in a data lake. So we have partition per data sets and some kind of partition per counter. So it will be efficient to query the data per counter. So we have a daily table, weekly table, monthly table, and that data is keep rolling, and we have like jobs running all the time for doing the aggregation, doing the anomaly detection, but eventually we're using a data lake. And so the data is stored in a data lake in an efficient manner, so we will be able to query it, and the best way to query data, and most efficient way to query data is using partitions.
Yeah. So on that one, can you give numbers, as in what's from source data, volume X, your final net volume of what you use, it's going to be less than X, but by how much in aggregate, roughly?
So you're saying the source data can be huge, for example, attacks, and eventually what we have I don't think that I ever tried to understand how much data we have daily from the data, but it's because it's only counter data. When we lose everything, for example, if we are saving requests, so we have post body and the query string and so on. When we are saving the number of requests, number of hourly requests, it's only a number, and it's together with a key. The key can be a URL, can be a CVE, but it's not even, I don't know, it's not, I'm sure it's very, very small comparing to the data, and we save the data for years. Because it's so small. So it's really nice because you can see trends over time for years. Like we can show customer trends over time for the, for example, for SQL injection, XSS, and so on, and of course for malwares, and because we have this kind of aggregation.
Thank you.
Thank you for the talk. Two small questions. First, is it everything is based on just HTTP traffic, or you have a way to handle HTTPS as well, encrypted traffic? And the second question is whatever you use only content or also metadata about requests, for example, kinds of fingerprints, etc.
So, it's mostly HTTPS, so modern day applications almost ubiquitously use HTTPS, so yes. And what was the second question again?
Do you use only the content of the request or also metadata about the request? And just to clarify the question about HTTPS, how do you handle HTTPS? How do you have visibility into the content of the request when it's encrypted?
Okay. So, do you know
so first, we, the sites that we protect are our customer sites, and they provide us with their certificates, and that's why we are able to parse it, and we see all the traffic. And we also see metadata, where, for example, we will see HTTP address, we will see, we have all the TLS fingerprints and everything, and that's why we can create counters for headers, for TLS. We have like, I haven't said that, but for example, we have TLS fingerprint, and we classify TLS, so we know about malicious TLS that we have, and so on.
And I think we have time for maybe one more question, if there are any. No? Well, in that case, thank you very much to Daniel Johnston and Ori Nakar.